Hello, this is Professor Keene. Welcome back to Introduction to Astronomy at Wisconsin Lutheran College. We've been looking at Aristotle's book On the Heavens. This is referenced in A Student's Guide Through the Great Physics Texts, Volume 3. We are in Chapter 3 of A Student's Guide right now. If you want to take a look at the specific text we'll be looking at, they begin on page 21 in A Student's Guide. This is Aristotle's chapters 10 and 11 and 12. In this chapter, chapter 10, Aristotle is addressing the question not merely of the motion of the stars, which again are fixed to this enormous celestial sphere that is rotating around the Earth, but also the motion of the sun and the moon and the planets. So I want to provide some more details about the complexity of the motion of those objects. So remember that the most simple motion is a motion of this enormous celestial sphere around the Earth. The idea is that the stars are fixed to the celestial sphere, it's rotating around so that the stars rise in the east and set in the west day after day. That is the east to west daily or diurnal motion of the sky. Now, what about the motion of the sun and the moon? They also daily rise in the east and set in the west. However, there's an additional complication for each of these. So in addition to that east to west daily motion, if one carefully observes the sun, one will notice that the sun also drifts from west to east over the course of an entire year. By that I mean that if you were to somehow get rid of the atmosphere so you could see the stars out during the day, and look at the constellation in front of which the sun is located, the sun will not be located in front of the exact same star constellation day after day. Rather, the sun will drift through the various constellations that make up the zodiac. So, for example, if the sun is right now in front of Aries, and it rises and sets in front of Aries, over the course of the next month, the sun will move eastward into the constellation Taurus. So, in addition to the east-west daily motion, there's a westward drift through the constellations of the zodiac, and through over the course of one entire year, it will go through all 12 signs of the zodiac and back to the original sign that it had been in 12 months ago. So there's superimposed on the daily motion, there's this retrograde motion or backwards motion through the sky. The moon also exhibits a similar kind of retrograde motion, but it's a bit quicker. So over the course of, day to day, the moon will rise and set. It'll rise in the east and set in the west, just like the stars, just like the sun. But over the course of 1 month, the moon will move in the west to east direction through the constellations of the zodiac once again. But it does this in only about 29 days instead of about 365 days. So again, the moon exhibits this retrograde motion, which is a complication. What about the planets? If one looks at the planets, they exhibit even more complicated motion. So they rise if you're looking at, let's say, Mars. If you're looking at Mars from night to night, it does rise in the east and set in the west, just like the sun, just like the moon, just like the stars, but it also retrogresses through the signs of the zodiac over the course of some period of time. But punctuating that, there will also be a progression through the zodiac. So sometimes it will be moving backwards, and sometimes it will be moving forward through the zodiac. It kind of zigzags back and forth in a complicated pattern. Jupiter does the same thing, Venus does the same thing, and Mercury does the same thing. So if the stars have the most simple motion, east to west, and the sun and the moon have a slightly more complicated motion, east to west plus west to east, the planets have extremely complicated motion, where on a day-to-day basis they go east to west, and then they also travel west to east through the zodiac, but sometimes they're moving east to west through the zodiac. So the question that Aristotle is interested in is, why is this? And he, following earlier astronomers Eudoxus and Callippus, believes in a mechanical model of the solar system, or he would say the system of the world, that can account for this complicated motion. So what I want to do is lead you through a couple of images that I've prepared to illustrate the kinds of motion and how Aristotle and the ancient Greek thinkers, and in fact the later thinkers like Ptolemy and the medievals, would account for the motion of the sun, the moon, the planets, and the stars. So I am entitling this slide Geocentrism, Aristotle, Ptolemy, who is a later Greek, Roman Greek North African astronomer, and the medievals. Okay, so here on the right-hand side of this diagram, of this slide, I show a diagram drawn by Peter Appian from his Cosmographia in 1524. So of course this is much later than Aristotle, but it captures the overall worldview that Aristotle and many of the Greeks and many of the medievals had. So you see here that you have the Earth at the center of the universe, and the Earth is of course made of earth. You've got water covering the Earth, at least parts of it, and then you've got air and fire above that. So you have these four elements out of which the sublunary or beneath the moon region is comprised. Then the first sphere up away from the Earth, you have Luna, or the moon. This is written in Latin, of course. So you've got the moon, the sphere of the moon, and then above that you have the sphere on which Mercury is riding. And then the sphere right above that, you have the sphere on which Venus is riding. There was actually some debate whether Mercury and Venus were above or below the sun. In this diagram, Peter Appian puts them below the sun. So the next sphere, of course, you have the sun, Solus. Above that, you have Mars, and then you have Jove, or Jupiter, and then above that, you have Saturn. And beyond that, you have the sphere of fixed stars. Of course, Uranus and Neptune and Pluto, for that matter, are not included here. Why do you think that is? Well, they were not visible using the naked eye until, well, not until people developed sophisticated optical instruments were those planets discovered. Okay, so outside of Saturn, then you have the sphere of stars. So that is the first sphere on the outside, you might say, that's undergoing this rotation on a day-to-day basis around the Earth, and the sphere to which all of the constellations of the zodiac and all of the other constellations are located. Peter Appian also supplements this with a few other spheres outside of there. There's debate about whether or not the heaven, where does God live? Are the heavens out there? What goes beyond that? The Empyrean. And so there's debate about that. Okay, so as I said, this diagram here is actually a bit of an oversimplification, but it schematically represents roughly the concentric sphere worldview that the ancients and the medievals adopted. And as I mentioned, this opinion was taken from the ancient Greeks. Eudoxus and Callippus developed this theory, and then this was popularized by Aristotle in the 4th century BC. It's good to note also that the ancient Greek astronomers were not unanimous on this worldview. So most notably the Pythagoreans, who we've had the occasion to mention once or twice before, the Pythagoreans rejected this worldview. They actually considered the Earth to be one of the planets like Jupiter and Mars and so on. Imagine that. They believed it was going around a central fire, that is, the Earth was in motion. Pythagoras predated Aristotle, and Aristotle actually considered this idea and then said, no, this is bogus. I don't believe that the Earth is one of the planets. After all, we feel like we're sitting still, and hence we are. So the idea of the Pythagoreans that the Earth is one of the planets is going to be resurrected much later in the 1540s by none other than Nicholas Copernicus, who argues for the heliocentric worldview that the Earth is one of the planets going around the sun, and he tries to be conservative. He says, well, maybe the Pythagoreans were onto something here and we rejected their ideas too soon. Anyhow, going back to the ancient Greeks, geocentrism was perfected, so to speak, by Claudius Ptolemy in the 2nd century AD, a bit after Christ, and he is much more mathematical than Aristotle was and comes up with a very sophisticated model that's based on the idea that the Earth is at the center, and it's excellent at accounting for the motion of the moon, the planets, and so on. You could make excellent predictions with this. Okay, now let's look a little bit more at the mechanism for this rotation. So we're going to step back a little bit. I have some diagrams here that schematically represent how this whole thing works. So the celestial sphere, which I've drawn here, is this enormous sphere. This isn't to scale, but I've shown the Earth at the center of the celestial sphere. And there is an axis running through the celestial sphere about which it is rotating on a day-to-day basis, right? So you can think about all these stars fixed to the celestial sphere. I don't depict them here so as to not clutter the diagram, but in any case, you should think about this as rotating around in the direction that's shown. It's important that it's rotating in that direction so that the stars rise in the east and set in the west. If you're perplexed by this, imagine the Earth, imagine the United States drawn on the Earth, and you want the stars to rise in the east, that is over New York, before they set in the west over Santa Barbara. Okay, and the North Star Polaris is on the north pole of this celestial sphere. Okay, now here I depict a couple of other lines. Specifically, I show the horizon line, which is a green dashed line that is tangent to the sphere, and then a line projecting perpendicularly from that points up to a point on the sphere that's called the zenith. So you might imagine if you're standing in the northern latitudes up here in Milwaukee, where we're located now, about 43, 44 degrees north latitude, if you were to be standing there, then there would be a plane that's tangent to the Earth, and one could see everything that is above this plane, any of the stars that were fixed to this sphere above, so to the right in that diagram. You could see the stars, and everything below that plane would be below your horizon and underneath you. Okay? And if you look straight up above your head, you follow that diagonal green dashed line that intersects the sphere at a particular point. That is your zenith. So if you were to point directly above your head right now, where you're pointing would be to the zenith point on the celestial sphere. Of course, that depends on where you're standing on the Earth, but you get the point from looking at this diagram. I also want to mention that if you imagine this celestial sphere rotating around while the Earth is sitting still, you can imagine that sort of circle along the celestial equator. Perhaps there's some stars right on that celestial equator. They're going to rise in the east, travel around, and set in the west. Okay? All right. What happens if you were to stand on the Earth but a little bit more southerly? So walk down to some place in Central America, let's say. When you do this, now you're standing closer to the equator of the Earth, and so your horizon line is tipped at a more vertical angle, and your zenith has dropped a little bit. But nonetheless, this sphere is spinning around once per day, so the stars are rising and setting. Notice once again that when they rise, they're coming out of the horizon at a slight angle and setting into the horizon at a slight angle as well. What would happen if you walked a little bit further to the south? Well, suppose you walk all the way down to the equator, like Quito, Ecuador, or someplace in Africa. If you did so, then you are standing right on the equator of the Earth, and so your horizon line, or horizon plane more precisely, would be straight up and down, be vertical like that. So you'd be standing with your head to the right in this diagram. So your zenith would intersect the celestial equator, and the North Star would be right just below when you look off to your northern horizon, the North Star would be right at the northern horizon, perhaps just below it. Notice here also that as the sphere rotates, the stars rise now out of the eastern horizon, coming straight up from your perspective. They go over through your zenith, and then they set straight down on your western horizon. Okay, so that gives you a feeling of the rotation of this celestial sphere for people standing at different latitudes on the surface of the Earth. Okay, let's go back to Milwaukee. Yep, here we go. We're back in Milwaukee. And once again, I have this horizon at this funny 44-degree angle right there. And now let's ask about the motion of the sun. After all, we're trying to account for this more complex motion, like the motion of the sun and the moon and the planets. We're going to focus on the sun here. So what I'm doing here is I'm supplementing this diagram by indicating a few of the constellations. Of course, there are stars all over this sphere, but there are certain constellations that are particularly interesting. Those are the constellations that form the zodiac. And those constellations reside along a line that goes around the sphere and is fixed to this sphere. So the one that's just off on the western horizon, if you're standing here, that would be Aries. This is Aries right here. Then we have Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. So if you were standing right here on the Earth looking off toward your western horizon, you would see Aries just right there. Okay. Now one should imagine that as this sphere rotates around, these constellations are fixed to it, so this whole circle of constellations rotates with the sphere. Okay, and that belt on which I've drawn them kind of like a line, but you have to imagine that those constellations take up, maybe 5 or 6 degrees above and below that line. By the way, it's called the ecliptic. Okay, now the sun, as we had mentioned before, always appears in front of one of these constellations. Whenever it's rising and setting, or whenever it's moving through the sky, it doesn't move randomly through the sky. It moves through these constellations over the course of the year. So what kind of mechanism could one imagine that would account for the motion of the sun through the signs of the zodiac? Well, here is the idea that the ancient Greeks had. Imagine that in addition to this enormous celestial sphere, this primary sphere, which is rotating around once per day, inside of that there's another concentric sphere that is also rotating on its own axes. Those axes are connected to the inside of this larger golden celestial sphere, as I've depicted it on this diagram. And the axle of that sphere is tilted at a funny angle, about 23 or so, 24 degrees. This inner celestial sphere, you might imagine as this big celestial sphere rotates around once per day, that inner sphere also rotates around once per day. You might imagine those axles, so it kind of wobbles as it's going around because it's fixed. Those axles are fixed up at this point right here and down at this point right here. So as this large celestial sphere rotates, this point is going to move around with it in a trajectory like this, and likewise this one moves around in a trajectory like that. And so what happens if the sun is fixed to this celestial sphere, it is going to rotate around as this larger celestial sphere is rotating around. But also notice that if we make this interior celestial sphere rotate independently in the opposite direction, then what happens if this rotates around once every year, that is going to account for the migration of the sun through the constellations of the zodiac. How does it do so? Well, that sphere is tilted at just the right angle so that as the sun moves around, as this inner sphere fixed, as the sun, which is fixed to this inner sphere, slowly rotates over the course of the year, the sun is going to appear in front of one of those 12 signs of the zodiac from the perspective of someone standing on the earth. So how does this work? So right now in this diagram, if you were standing on the earth and to look outwards at the sun, ignoring the horizon for a moment, if you were to look outside at the sun would appear in front of the constellation, maybe Pisces, or between Pisces and Aries. Okay? But as the sun, as this interior sphere rotates around, eventually it'll get to the point where the sun will appear in front of Aries, and then in front of Taurus, and then in front of Gemini, and so on. This is depicted in the following diagram right here. So this is if the sun is right at the first point of Aries, so it appears from the perspective of someone on Earth that the sun is in front of the first point of Aries, on that day of the year, as this large sphere rotates around once per day, the sun is going to be moving around in this trajectory from the perspective of someone who is watching from the Earth. But once this inner sphere has rotated around enough over the course of, let's say, 3 months or so, now the sun is up here on this interior sphere. If you're looking from the perspective of Earth outward, the sun is going to appear kind of over here between Gemini and Cancer. Then, over the course of one day, the sun will appear to go around in this circle right here as this outer sphere rotates around. Then, if you wait 6 months later until this inner sphere has rotated around another half a revolution, now the sun will appear to be between Sagittarius and Capricorn. Then, over the course of the day, as this big sphere rotates around day after day, it will be following this trajectory. So you can see by this two concentric sphere model, one can account for not only the daily or diurnal rising and setting of the stars and the sun, but you can also account for the drifting of the sun through the constellations of the zodiac over the course of the year. So notice that this is somewhat complicated, but it's not overly complicated. It is able to account for the essential features of the motion of the sun. Now keep in mind that here we're only referring to the motion of the sun. you might imagine that there are going to have to be additional spheres, concentric spheres, to account for the motion of the moon and its drift through the constellations of the zodiac over the course of a month. Furthermore, one must have a series of extremely complicated series of concentric spheres to account for the individual motions of the planets through the zodiac, both forward and backward, with these complex patterns over the course of their years. Okay, so you can see here how this model ends up becoming a quite complex model, but on the other hand, if you make these spheres just the right size, if you imagine them to be just the right size, and if you imagine these spheres to be rotating at just the right rates, one could in fact account for the complex motions of all of these celestial objects. That is, this model, as they would say, saves the appearances. This model makes predictions that match the data. And this is going to work very well. This kind of model is precisely the model that was adopted by the ancients and was carried over in the Middle Ages, just about to the time of Tycho Brahe and Copernicus. Why don't we stop there and we'll pick this up next time.